Let's recall a few more definitions from set theory that also apply to probability and to our experiments. So the union of two events, E and F, is the set of outcomes in E or F or both. Same definition for a union, we just apply it to events. Same goes for the intersection of two events, that's the outcomes that are in both E and F. And the idea of being mutually exclusive would mean that your two events have nothing in their intersection. They do not have any outcomes in common. So all those definitions still apply when we move from set theory to probability. Now, the relative frequency method for doing probabilities. I accidentally made a line here when I didn't need one. Is probably what you think of when you originally think of probability. The probability of an event occurring is a measure of the proportion of the time that E will occur in the long run. We use P of E, or P parentheses E close parentheses, as the notation for the probability of an event E. Okay, so basically you divide your outcomes in order to find probabilities. The probability of an event is a number that lies between 0 and 1 inclusive. So a lot of times we give our probabilities as their decimal format, and their decimal format will be always something between 0 and 1. As percentages, that's between 0% and 100%. You can't have a probability that's less than 0, no negative probabilities. And nothing will ever have more than a 100% probability. 100% means it's guaranteed to happen, and there's nothing beyond that. If E happens to be the empty set, then the probability of E is 0. So again, you have to watch your notations here, because an event can be an empty set, but the probability of that event has to be a number, which would be 0. So watch your notations. To find the probability that an event E will not happen, you will take 1 minus the probability that it does happen. So 1 minus the probability of E. That's because we know, again, from our set theory, that if you have the probability of E and you add E complement to it, then we have to get 1, or all of the possible outcomes. If E is an event in a sample space S, and S has equally likely outcomes, then the probability of E can be calculated by P of E equals the number of outcomes in E divided by the number of outcomes in S. Or what we could say in our set theory idea is the number, or N of E, the number of elements in E, divided by the number of elements in S. So this is probably what you think of when you think of probability without ever knowing maybe the formal definition for it. I would take the number of outcomes that I'm interested in, divided by the total amount of outcomes that could happen, and divide that out, and that would give me my probability. One more definition is the idea of a simple event. So a simple event are the subsets of S that contain exactly one sample point. Simple events of experiments are mutually exclusive, and if you add up all their probabilities, you have to get 1. So for instance, let's scroll back up in our notes. If we go back to very number 1, event E, the spinner pointing at the color purple, that would be a simple event, right? It only contains a single element. Whereas F has 2 elements, so that would not be considered a simple event. So each one of the colors individually would be a simple event, and if we added all of those up, we would get a probability of 100%. That's the whole spinner. So that's the idea of what a simple event is. Okay, so let's do a few probabilities now that we've got a lot of our definitions written down. So it says you're going to reach into a bowl without looking. The bowl contains 5 red dice, 3 green dice, and 2 white dice. And we are going to find the sample space, the probability of drawing a red, the probability of drawing a green, and the probability of drawing a white. Okay, so the sample space here is just R, W, and G. Those are the three different outcomes that you could observe when you draw here. What's the probability of drawing a red dice? Okay, so remember you have to take the outcomes that are favorable for that divided by the total number of outcomes. So there are 5 red dice. That's going to go on the top. There are 5 ways that you could choose a red dice. Out of, what's the total amount? Well, there are 10 total die in that bowl. So 5 out of 10 is the probability of a half. So there's a 50% probability when you reach in there and draw that you would draw out a red die. What about green? What's the probability of drawing a green? Well, we're still drawing out of the 10 total, but there are only 3 green die. So that would be a 30%, or we could write that as 0.3. All of those are acceptable ways to write these. Pay attention to how the question asks you online. The probability of drawing a white. Well, there are 2 out of the 10, which reduces to 1/5. So I can either leave that as a 1/5. I could divide it out and get the decimal 0.2, or I could give that as 20%. And all of those are acceptable ways to write it. And it says, notice each of these are simple events of the sample space. Right? Drawing a red, that's one element. Drawing a green is one element. Drawing a white is one element. And if we add up all those probabilities, if we add them up, I'm going to add up their decimal forms. So if we add up 0.5 plus 0.3 plus 0.2, we get 1. So that just verifies this rule that if we add up all of the simple events, all their probabilities, we should get 1. Like there's a 100% probability that you're going to do one of those things. Okay, a fair die is rolled. What is the probability that it will come up? Okay, so what might be helpful here, it's not asked of us, but what might be helpful is to write our sample space before we start doing probabilities. So if you roll a die, you could get a 1, 2, 3, 4, 5, or 6. So that makes up our sample space. Those are the outcomes we could observe. So what's the probability that it will come up odd? I'm going to call this P of O for the probability of odd. And I want to make a fraction. I usually go to the denominator first, honestly. There are 6 different outcomes that we could observe. How many of them are odd? So there are 3, 1, 3, and 5 are all odd. So there are 3 ways out of the 6 to draw or to roll an odd. So 1/2 would be the probability of rolling an odd. That seems pretty logical. Okay, what's the probability of it being less than 3? So I'm going to call this P of less than 3. Again, the denominator is still 6 because there are 6 possible outcomes. I'm going to switch my color here. How many of these outcomes are less than 3 strictly? That would only be the 1 and the 2. So there are 2 ways that we could roll a number less than 3, and that reduces to a third. What's the probability that we roll a number both odd and less than 3? So I'm going to call this the probability of O and less than 3, intersect less than 3. So if I look, what's helpful is that I've underlined these. If I want to find the intersection of those, notice that it's just the element 1. 1 is the element that got underlined both times. So there is one way to roll a number that is both odd and less than 3 out of the 6 total elements in the sample space. And that doesn't get reduced. It can't reduce, so just 1/6. What's the probability of rolling a number odd or greater than 3? So odd union of greater than 3 in this case. So we flipped it. Okay, so I'm going to go ahead and erase my lines here. Okay, so I'm leaving the odd ones underlined, the 1, 3, and 5. And then what about greater than 3? Greater than 3 would be the 4, 5, and the 6. So if I want to add these up, basically, remember or is the inclusive or, so the or both also counts. Remember the probability of rolling an odd was 1/2. The probability of rolling a number greater than 3 is also 1/2. So it's 3 out of the 6 total. But I can't just add these up. The probability of rolling an odd or greater than 3 is not 1 because I have overlap. So I can add these up, but I have to subtract off the intersection. So where are the numbers that are both odd and greater than 3? That's this 5. So there's one way that I could do both, and that has been double counted so far. It was counted in the odd, and it was also counted in the greater than 3. So we have to subtract that off. So 1/2 plus 1/2 gives us 1, but then we subtract a 6th off of that, we should get 5/6. So make sure you don't double count. What's the probability of rolling a number less than 3 or greater than 5? Okay, so I'm going to erase these lines here. So if I roll some number less than 3, that could be 1 and 2. So there is a 2 out of 6 ways to do that. And greater than 5 is only the number 6, so there's 1 out of 6 ways to do that. And there is no overlap, so I would just subtract 0 from that. So 1/6 plus 2/6 is 3/6 or 1/2. So just as a reminder, if E and F are mutually exclusive events, then to find the probability of their union, you simply add the two probabilities together. Because if they're mutually exclusive, there is no overlap. But if they are not mutually exclusive, then to find the probability of their union, you have to add the two probabilities together and subtract off the probability of their intersection.